Okay, so we shall start off in chapter 10 by looking at energy and its various forms. We shall think of energy as part of a system. Our system can consist of various objects, and it can be a closed system or an open system. A closed system is one that is insulated from the environment, and an open system is not. So what we've done right now is just define what we mean by a system or an energy system. And then we can also look at the various forms of energy that are part of the system. So within the system, there could be all forms of energy, and we shall list a few of them. These forms of energies are, first we can call kinetic energy. This is energy associated with an object's motion. Number two, we have potential energy. This is a stored energy that is due to an object's position relative to a reference point in a field. We can also have thermal energy. This is the energy of random motions of atoms within an object. We can also have chemical energy due to chemical bonds holding compounds or atoms together. Nuclear energy, energy within the nucleus of an atom. I could go on and on with different forms of energy, but I think I'll stop here and just go on with our lecture on energy. So this is not an exhaustive list of all the various forms of energy that we can have, but I think this is good enough for now. And we can think of our system as containing various forms of energy. Within our system, the energy can be transformed from one form to the other, but the total energy of the system does not change if the system is close to the environment. So that's an important point to keep in mind. So I'll make a note here. We should also note that energy can be transferred from one system to another, or can be transferred from outside a system into a system if the system is open. So I'll make that note also. So in an open system, energy can be transferred in or out, or into or out of the system, or between systems. So what we've learned right now is two concepts: energy transformation, where energy can be transferred from one form to the other, and energy transfer, where energy can be transferred into or out of a system or between systems. When I talk of energy transformation, what I mean is energy can be transformed, for example, from kinetic energy to potential energy. So I'll make a note of that here for you. So energy transformation means, let me show you a few energy transformations. So this would be examples of energy transformations. So we can have kinetic energy to potential energy. We can, of course, go from potential energy to kinetic energy. And then we can also have kinetic energy to thermal energy, and from thermal energy to kinetic energy. And this is not only the list of energy transformations that you can have. There are multiple energy transformations. I'm giving you just these few energy transformations as an example. You can also have kinetic to potential to chemical and so on. So there are multiple energy transformations that you can have. What it comes down to is that all forms of energy can be boiled down into two forms: kinetic energy and potential energy. Let's look next at kinetic energy and potential energy, and we shall look specifically at the gravitational potential energy. This is in section 10.2. So let me write it out as kinetic energy and gravitational potential energy. Let's consider an object of mass m that is falling from an initial position y subscript I to a final position y subscript f in the gravitational field. We will label the object's velocities as initial v to be vi subscript y and v final subscript y within its position. So let me draw that to start off. So let's say this is an object of mass m, and it falls from an initial position. This is the initial position y subscript I to a final position y subscript f, and it has initial velocity vi subscript y and a final velocity vf subscript y. So we are using the subscript y, as you know, because the object is falling in the y direction or vertically. We can start off by using our kinematic equation. So let's use V final y squared equals V initial y squared plus 2a subscript y delta y, where we can say that delta y is equal to y final minus y initial, and a subscript y is the acceleration of gravity, and we can use we're using acceleration of gravity a subscript y to be minus g. So our formula v final y squared becomes v initial y squared minus 2g y final minus y initial. This analysis was derived from using our kinematic equation, and what it really gives us is a form of the conservation law for free-form motion. So we can multiply through by the mass and divide by 2, and we will see that we end up with a form of equation which is basically a conservation law formula. But let's go on and derive this with a more general technique, which would allow us to arrive at a similar formula, but we're using a different approach. So let's consider Newton's second law along the y-axis. We shall say that the net force on this object along the y-axis is equal to the mass times acceleration along the y-axis, which we can then write as m times dv in the y direction dt. So we can, this is our form of Newton's second law along the y-axis. The net force on this object is just equal to its weight, so we can say that the net force in the y direction is equal to weight, which is minus mg, because remember that the gravitational force pulls downward, so we're using the negative vector for that. So we shall say m dv in the y direction dt is equal to minus mg, and we'll make a transformation which will make it easier to do this analysis. We will say that so let's use the following rule. You will recognize this as a chain rule, and the chain rule just tells us that dv subscript y dt is equal to dv subscript y dy times dy dt, which can then be written as v subscript y dv subscript y dy. So let's now substitute this into our formula above, and we shall have m v subscript y dv subscript y dy equals minus mg. And then integrating both sides, we'll have the integral m v subscript y dv subscript y to be equal to minus mg, and then we are integrating dy. So the integrals go from v initial y to v final y, y initial to y final, and this leads to half m vy, then we have v initial y, v final y, and that will give us half m v final y squared minus half m v initial y squared, and that should be equal to minus mgy y initial y final, and that will give us minus mgy final plus mgy initial. So this leads to the following formula, which is written as half m v final squared plus mgy final to be equal to half m v initial y squared plus mgy initial. So this is a way of saying that the final total energy is equal to the initial total energy. So we can list it that way. This is final total energy, and this is initial total energy. This equation that we've just obtained above is similar to the one we started off with, the one we first found by using the kinematic equation above here. So I'll show you how the two are similar. First, multiply through by m and divide by 2. So by doing that, we shall have mv final y squared equals mv initial y squared minus 2 mg, then we have y final minus y initial. Now dividing by 2 gives us half mv final y squared equals half mv initial y squared minus mg, then we have the y final, let's do it this way, plus mg y initial. And then rearranging gives half mv final y squared plus mg y final to be equal to half mv initial y squared plus mg y initial. As you can see, this is the same as what we had above. So let's define the quantities we just found in these formulas. So let's look at what is called kinetic and potential energy. So in our above formulas, let me just say in our formula or formulas above, half mv squared is equal to kinetic energy and mg y is gravitational potential energy. Energy is a scalar quantity with a unit of joules in the SI system. All forms of energy are measured in joules in the SI system. So chemical energy is also measured in joules, nuclear energy in joules, potential energy, gravitational and kinetic are all measured in joules. We note that 1 joule of energy is equal to 1 kilogram meters squared per second squared, like that. Let's look next at defining the zero of potential energy. Note that since we mentioned that potential energy is an object energy relative to a reference point, that we can take that reference point to be zero potential energy. We shall use this concept of a reference potential energy or zero potential energy in the next section when we take a closer look at gravitational potential energy. So this is section 10.3, gravitational potential energy. So gravitational potential energy is the energy an object has due to its position in the gravitational field, and it's a stored energy. Let's analyze the motion of an object moving along a ramp as a way to understand the concept of gravitational potential energy. So I'll draw the ramp this way, and we start off with the object in this position along the ramp, and we can say that it has initial velocity v subscript I, and it ends up here along the ramp with final velocity v subscript f. The forces on this object can be labeled here, so I'll draw that separately so that I don't get too many things into one diagram. We have the weight acting vertically downwards, of course, and then we have the support force, which is the N pointing that way, and then there is a velocity acting on this object that is causing it to move. So as it's moving up, we point it up that way. The ramp has angle theta, and we can say that the distance along the ramp can be given by S. Let's call this ds, of course, and then this height is dy. Angle is theta, so dy can be written as sine theta ds. So that will come in useful for us as we analyze the motion of this object as it goes along the ramp. So we start off by saying that the axis parallel to the direction of motion is the s-axis. So our net force along s is equal to the mass of the object times acceleration in the s direction, which we can say is m dv subscript s dt. We use our chain rule again like what we did before. So the net force along s can be written as m dv in the s direction dt, which can be written as m dv in the s direction, the ds, hold on a second, ds times ds dt which can then be written as m v in the s direction dv subscript s ds. Note that we've used v in the s direction v subscript s to be equal to ds dt. Now back to our diagram. One of the forces that will be acting along this object will be the gravitational force or the weight down the ramp. This would be called F net in the S direction. This is the force along the ramp. So the net force in the S direction along the ramp is equal to minus the weight, which is mg, times the sine of the angle, sine theta. So we can now say that minus mg sine theta is equal to mv subscript s dv subscript s ds. From here we can continue our analysis. Let's rearrange it. mv subscript s dv subscript s can be written as minus mg sine theta ds, and then you can integrate both sides. Before we integrate, we note that sine theta ds is equal to dy. So we shall have mv subscript s dv subscript s equals minus mg dy. Now we can integrate both sides from v initial to v final dv subscript s, and we have minus mg y initial y final dy, and this leads us to have mv subscript s. We have our v initial, v final, and we have minus mg y initial, y final. This will lead to the same formula as what we had earlier, half mv final squared plus mg y final equals half mv initial squared plus mg y initial, which is just telling us that the total final energy is equal to the total initial energy, which is a form of conservation of energy. We can say then that the forms of total energy, let me start off. We can say that the formulas found above represent the conservation of energy principle, where we have total initial energy equal to total final energy. So this brings us to the conservation of energy principle, and let's write it this way: conservation of mechanical energy. Let's write mechanical energy to be E mech that way. We can say that the total mechanical energy of a system is just the sum of the kinetic and potential energies. I already mentioned earlier that all forms of energy can be boiled down to total energy being kinetic energy plus potential energy. So when we talk of mechanical energy, we are referring to the sum of kinetic energy and potential energy. In this formula, Ke is kinetic energy, obviously, since I already mentioned that, and Pe is potential energy stored in the system. So this is the total mechanical energy of the system. If the system is closed, then any change in total mechanical energy is equal to 0. Change in mechanical energy is written as delta mech. That should be equal to 0. This means the energy of the system is conserved. So changes in total mechanical energy can be written also this way. This can be written as change in kinetic energy plus change in potential energy, and that should be equal to 0. So what this tells us is that the change in kinetic energy is equal to the change in potential energy minus the change in potential energy. So a loss in kinetic energy is equal to a gain in potential energy, and so on. So we can write it this way: change in kinetic energy is equal to final kinetic energy minus initial kinetic energy, and change in potential energy can be written as final potential energy minus the initial potential energy. Therefore, if we write Ke final minus Ke initial to be equal to negative Pe final minus PE initial. Then what we will have is kinetic energy final plus potential energy final is equal to potential energy initial plus kinetic energy initial. This is what we found above. So this again brings us to our previous analysis where we've shown that the total final energy is equal to the total initial energy. This is just what we've been finding all along during the course of this lecture. So this is the end of this lecture. We shall continue next week.